Hello. So for our project, we will go through the process of building, training, evaluating, and tuning the convolutional neural networks for image classification using CIFAR dataset. So basically, this dataset is huge, and this contains more than 60,000 images, and with 10 distinct classes. So basically the goal is to optimize the model's performance through effective data pre-processing and augmentation and hyperparameter tuning. So let's start by our code. We started by importing the necessary libraries such as the Keras library for building the neural networks, Matplotlib for plotting the CIFAR dataset, and this dataset is used for training and testing the data. So here we didn't download the data because it's huge and it will take so much time and space. Here we gave a size 10 for our indices, and we mapped the labels. We have here from 0 to 9, and we give examples of this data. We have cat, dog, horse, etc. Then we randomly labeled and plot the images, and we used here a 2 by 5 matrix, and we can see here some images from our dataset for the data we put here. Now let's move. Again, we will repeat the process of loading the data, normalizing the pixel values, and make them between 0 and 1. Then we convert the vectors to binary class matrices, and we have the data augmentation application that is used to improve the model's generation. And we have some techniques such as the rotation, width shifts, the height shifts, and zoom range, etc. And the augmented data is then fed to the training set. Now let's move to defining our model with batch normalization. So basically it consists of multiple convolutional layers followed by batch normalization activation, and we have the redo here, the max boolean. We have also the dropout layer, and the flattened output from the convolutional layers is fed into dense layer, and this layer is used for classification. And now let's move to here. We compile our model. So the model is compiled using the Adam optimizer, and we have the learning rate scheduler that is used for early stopping callbacks, and they are defined to adjust the learning rates during the training and stop the training also early if the validation loss, for example, does not improve to our number of epochs, because epochs here are important. Here we plot the accuracy. We can see this graph that represent the accuracy and the number of epochs, and basically here we had 5 epochs. And here we have the loss plot. So for measuring the model performance with the F-score, here we imported the F-score, and we evaluate the model on the test set, and here we have values of loss and the accuracy, and we have 3 seconds per epoch. Then we have the calculation of the F1 score, and then we print the test accuracy and the test F1 score, and we can see that we have those values. The test accuracy is 0.6004, and the test F1 score is 0.5783. So let's move now to if we want to add a new layer and the introduction of the learning scheduler callback. We will go through the same process, and by loading the data, importing the libraries, loading the data, normalizing the pixels to have the values between 0 and 1, and now we have the data augmentation. Again, we have the height, we have the rotation, we have those parameters, and we define our model with batch normalization. And we compile our model, and we have the learning rate scheduler here. And here we have the number of epochs is 5. So when the number of epochs finished, we have to train our after training our model, we have to plot the validation and the accuracy of our model. We can see we have this graph. We have the number of accuracy that go from approximately from 0.51 or 52 or maybe 53, and then it goes, and we can see the number of epochs here. Then we have the plotting for the training loss and validation. Then we go through the same process of loading the data. Here, importing the libraries, and we train our model. We compile the model using again the Adam optimizer, and we define the learning rate scheduler. We train the model, and we save the file in the model my model.h5 file for a future deployment, for example. And again, we train. We have the plot for the accuracy and validation. We have this plot for the loss that is decreasing, and the validation loss it starts increasing from 3 when in the epoch 3. Now let's move to, if we want to make predictions on different number of batches and computing the overall accuracy. Again, we have to train, we have to load our data, we have to normalize the pixel value to become between 0 and 1, and then we have the two we have the x we So here we load the predefined pre-trained model that we saved in this file, and we label the mapping. We have the images and their indices, and we have the same data that we used. So we choose a random index. Here we have index 2, and here we can see this image. Now let's move. We have the predicted labels batch. This corresponds to the mapping of the predicted class to the labels. Here we calculate the accuracy for each prediction, and we print those predictions for the batch. Here we can see in the result we have the image 1, image 2 to 5, and we can see that the accuracy is 1 for automobile. So here we calculate the overall accuracy, and here we have the overall accuracy is 20%. Now for the hyperparameter tuning, again we load the dataset from CFR10. We normalize the pixels to become from 0 to 1, and we convert the classes vector to the binary class matrix. For the data augmentation, we still have these parameters, the same parameters we use, the rotation range, the height shift, etc. And we prefetch the data batches to improve the data loading efficiency. Here we have 265. Now here we put all this code in one cell because we repeat the same process, normalizing the pixels. We load the data, we import the libraries, we convert the classes vectors, and we have the data augmentation to and improve the data loading efficiency. We train, we build our model, we define it basically, and we have the learning rate, and we have the optimizer. Here is Adam optimizer. Then we initialize this. What is new here is we initialize the tuner. So basically, we initialize the tuner, and we define the hyperparameter tuning, and then we go to look for the best hyperparameter and the model that is with the best hyperparameter, and then we train the model with these with the best hyperparameters we found. So here we can see that we did 10 trials, and the accuracy value is this, and the number of epochs was 5. So again, we repeat the same process by importing the libraries, loading the dataset, and the data augmentation. And here the hyperparameters from the images, we give some filters, and here we have the learning rate. We build again the sequential model. We define it, and we compile the model, and we have the learning rate scheduler, and we train the model and we save it in the same file. Here the number of epochs is 10. Okay, so the number of was 10, and it increased to 40. Here we have the plots for the accuracy and the epochs, and here for the loss, the train and validation loss graphs. Now let's move to training the model with hyperparameter tuning. We import the libraries, the necessary libraries, and we load the model from the file where we saved our predefined model. So we plot the accuracy. This is the accuracy graph. Well, the accuracy and the number of epochs. We can see that the train accuracy is in blue and the validation accuracy in orange. And this graph is to represent the training and validation loss. We can see that they are both decreasing. And now let's move to the hyperparameter tuning with number of batches and number of epochs. We load the data set. We have the data augmentation, the hyperparameters from the image, and here we defined different combinations for the number of epochs and the batch sizes. But the number of epochs is 5. And we have the plot setup, and we build our model here. We compile the model. We use again the NADM optimizer, and we set the callbacks. We train the model, and then we plot. So we can see that this graph is going from 0 to 4, number of epochs, and we plot the accuracy of the loss. Sorry, this is the accuracy the graph, and this is the loss graph. So here again we load the dataset, we convert the classes vector to binary, and we load the predefined pre-trained model. So the model was defined and pre-trained. Now we use the label mapping. We have the same data and the indices from 0 to 9, which is 10 indices. We choose a random index. Here we have index 2, and we make predictions using the loaded model for the batch of images. Here we map the predicted class indices to the labels, and we calculate the accuracy of each prediction, and we print it. And here we have the calculation of the overall accuracy. Here we found 80%. And then we will go through the same process by importing the libraries. We load the dataset. We convert class vectors to the binary classes metric. And we load the pre-trained model. We calculate the accuracy for each prediction, right? and we calculate the overall accuracy for the entire test set, and we have here the overall accuracy for the entire test set is 79.85%. Here, in order to generate the confusion matrix, we import the confusion matrix and we define the function here, and we display our confusion matrix. We can see that we have here the true labels, the predicted labels, and we have the different values for our pre-trained model.